For a couple special cases for energy, we're going to start off with space. You can use your statement of conservation of energy where you have gravitational potential energy and kinetic energy, both in the beginning and in the end. And you can set those two equal to each other to find your orbital speed. You can also set initial kinetic energy equal to final gravitational potential energy to find your escape speed. Or switch that. Final kinetic energy equals initial gravitational potential energy to find escape speed. A geostationary satellite means the satellite has the same period and angular velocity as the Earth's orbit, so it stays in one place. If it's flying overhead New York City, and New York City is rotating, that satellite is going to rotate at the same rate and stay over New York City. K equals negative 1/2 U sub big G, and total mechanical energy for your orbit is going to be 1/2 U sub G. Kepler's first law says all planetary orbits are ellipses. Kepler's second law, we're doing equal sweeps in equal time, which means it moves faster when it's closer to the object it's orbiting. And Kepler's third law, t squared is proportional to r cubed, can be proved by setting f sub big G, gmm over r squared, equal to m times v squared over r. Remembering that velocity for things traveling in a circle is 2 pi r over the period. For elliptical orbits, first try using conservation of energy, and for circular orbits, first try using Newton's second law, which is first drawing your free body diagram and then using the stuff that makes it go minus stuff holding it back equation. For AP Physics C, F equals negative du dx. Don't forget the negative sign. This also tells us that if we were to plot a potential energy versus displacement graph, then the slope of that is going to be our force. More on that graph later. For springs next to each other, like that, we're going to have an effective spring constant, and that's just going to be K1 plus K2. And we can use that either in the spring force equation or the elastic potential energy equation. And for springs that are in line with each other, stacked one on top of each other, we're going to find the inverse of our effective spring constant being equal to the inverse of our spring 1 spring constant, and then the inverse of the spring 2 spring constant added to that. Don't forget to take that inverse at the very end after you add those two inverse spring constants.